Welcome to this explainer. I'm absolutely thrilled to take you on a journey today that strikes at the very heart of how we understand our reality. We're taught from a super young age that the fundamental laws of physics are set in stone, that the rules governing the cosmos are absolute, unwavering constants. But what if they aren't? What if the fabric of the universe, and even gravity itself, is actually evolving as time ticks by? Today, we're exploring the brilliant minds who dared to challenge Albert Einstein's established laws of gravity.
To plunge right into this cosmic mystery, I want you to imagine a staggeringly huge number. 10 to the 40th power. That's a 1 followed by 40 zeros. Take a second to let the sheer enormity of that sink in. We're talking about a mathematical coincidence so profound that it perfectly bridges the gap between the microscopic realm of the atom and the unimaginably vast edge of the observable universe. How could a connection like that possibly exist?
The magic of cosmic numbers.
Okay, so let's break down this mind-boggling scale that absolutely obsessed brilliant 20th century physicists like Paul Dirac. Dirac noticed something uncanny. If you take the ratio of the electrical force to the gravitational force between a proton and an electron, you get roughly 10 to the 40th power. Now, if you take the estimated radius of the entire universe and divide it by the microscopic radius of an electron, you get a number in the exact same order of magnitude, roughly 10 to the 40th. To Dirac and earlier thinkers like Weil and Eddington, this wasn't just some random math quirk. It was a glaring signpost pointing toward a deeply hidden connection between the quantum world and the macrocosm.
This astounding mathematical coincidence led directly to Dirac's famous large number hypothesis. He proposed a totally radical idea. To maintain this exact ratio as the universe constantly ages and expands, the constants making up these numbers, well, they couldn't actually be constant. He hypothesized that the gravitational constant, the big G, must actually decrease over time. Simply put, as the universe gets older, gravity actually gets weaker. It was a revolutionary idea that completely defied standard physics.
Section 2. Mach's principle and inertia.
Now, to truly understand why top-tier scientists wanted to rewrite the rules of gravity, we need to look at a profound philosophical riddle about motion from back in 1883. It comes from Ernst Mach, a philosopher and physicist who deeply influenced a young Albert Einstein. Mach argued that the local inertia we feel, that heavy physical feeling of being pushed back into your seat when a car accelerates quickly, isn't just an isolated thing. He believed it's secretly governed by the distant collective masses of the entire universe. Basically, your local motion is inextricably tied to the distant stars. This idea is absolutely wild, right? And this ongoing academic pursuit to embed Mach's philosophical ideas into the hard, rigid geometry of spacetime has completely consumed physicists for decades. Einstein himself actually tried to incorporate this into general relativity, famously attempting to show how the presence of distant bodies might explicitly affect the mass of something local.
Think of Mach's principle like this. It suggests a fascinating thought experiment. If the universe were completely empty except for one single object, that object wouldn't possess any inertia at all. You couldn't tell if it was spinning or moving straight because there'd be no background matter to reference it against. Just let that linger for a second. No background universe, no inertia. Einstein found this deeply fascinating, but ultimately, pure general relativity leaves it out. In Einstein's math, inertia is just an intrinsic local property, not something dynamically generated by the rest of the universe.
Section 3. Challenging Einstein. Brans, Dicke.
So, if general relativity doesn't fully capture Mach's principle, how do we modify it so that it does? Well, this is where we see a massive clash of ideas. On one side, we have Einstein's static gravitational constant. It's firmly fixed, unchanging, the exact same today as it was billions of years ago. On the other side, we have the evolving, fluid, time-varying gravity initially proposed by Dirac, which was later developed into a highly competitive mathematical framework by Carl H. Brans and Robert H. Dicke in 1961.
In the Brans-Dicke scalar-tensor theory, they didn't just throw out Einstein's work, they added to it. They introduced a universally coupled scalar field that works right alongside Einstein's curved spacetime. I like to think of it like a cosmic dimmer switch for gravity. What this effectively means is that gravity's strength isn't a constant at all. It's a value that weakens or strengthens depending on the overall distribution of matter in the universe. It was a really elegant way to finally force Mach's principle into a relativistic framework.
Section 4. The Hoyle-Narlikar alternative.
But, Brans and Dicke weren't the only ones trying to rewrite the cosmic rulebook. Enter Fred Hoyle and J. Narlikar. They proposed a gravity theory that is completely radical by today's standards. They wanted to cancel the Big Bang altogether. No way, right? In their model, the universe is eternal, existing in a quasi-steady state. To keep the density of the universe constant while it expands, they propose that gravity's strength is tied to that mean density, and that matter is just continuously being created out of empty space. They envisioned these continuous mini-bangs happening at the centers of massive quasars, generating new matter via what they called creation fields, or C fields.
This matters profoundly. Why? Because both Dirac's hypothesis and Hoyle's theory fundamentally require the continuous creation of matter, whether it's happening subtly everywhere or violently in specific cosmic hotspots like quasars. Taking this path completely shatters the standard Big Bang narrative of a single, definitive moment of creation. It forces us to imagine a universe that's just endlessly replenishing itself to keep its physical laws in perfect balance.
Section 5. Testing the gravity rivals. Of course, theoretical physics is undeniably beautiful, but eventually every great theory has to face the harsh, unforgiving judgment of real-world astronomical observation. To figure out if G was actually changing, astronomers basically turned the cosmos into a giant laboratory. They measured the incredibly precise cooling of dead white dwarf stars, they analyzed colossal supernova explosions, and they timed the dizzying clock-like spins of binary pulsars. They even bounced lasers off mirrors left on the moon to measure the Earth-Moon distance down to the millimeter. If gravity was weakening over time, these extremely precise scales would absolutely show it.
So what did the data actually say? Well, the results from these insanely rigorous tests showed that if the gravitational constant G is changing at all, the variation is infinitesimally small. We're talking about an upper bound of around 10 to the negative 11th power per year. That means any change is so microscopically slow that, for all practical purposes, it's basically static.
Because of these incredibly accurate measurements, mostly made from the late 1970s onward, the scientific community came to a pretty clear conclusion. The Brans-Dicke theory, despite brilliantly incorporating Mach's principle, just fares no better than the simpler, standard theory of Einstein's general relativity when we test it right here in our solar system. Einstein's static constant held strong. The reigning champion of physics remains undefeated in our local neighborhood,
And the Hoyle-Narlikar theory, it hit a massive observational wall too. Data from the WMAP satellite mapped the cosmic microwave background radiation, literally the thermal afterglow of the universe's creation. This radiant echo strongly challenged their eternal, steady-state hypothesis. The thermal footprint of the cosmos matched the Big Bang model perfectly, which left the continuous creation theories really struggling to align with the hard, cold facts. But don't count these brilliant rivals out just yet. Science is never entirely settled, and a new mystery has opened up. The relatively recent discovery that the expansion of the universe is actually accelerating, driven by a mysterious force we call dark energy, has thrown a massive wrench into standard cosmology. This weird twist has actually renewed theoretical interest in scalar field modifications to general relativity. The mathematical tools built by Brans, Dicke, and others are actually finding new life right now in modern string theory and inflationary models.
Which brings us to our final, provocative thought for this explainer. As we desperately try to understand the true nature of dark matter and dark energy, which together make up over 95% of our universe, will we be forced to revisit these alternative models? Will the ultimate theory of everything require us to finally weave Mach's vision of a deeply interconnected universe into the rigid fabric of Einstein's spacetime? Thank you so much for exploring the evolving rules of the cosmos with me today. Keep questioning and keep looking up.